Check, check. 1, 2, 3. Check, check, check. Good morning. Good morning. Shoot, I need my drink. I'll be right back. There we go. Cats are very interesting creatures. You can't really teach them to play fetch, but that doesn't mean they can't and don't play fetch. Like this one, Rimmy. She'll take one of my wife's hair elastics and bring it up onto the couch and expect me to throw it for her, and then she goes and chases it and brings it back. And under normal, like, if that were a dog, that would be playing fetch, but I could, like, she's learned that if she brings it to me, I'll throw it for her, but, like, I can't initiate fetch, you know? I can't, like, grab the object and be like, fetch time? Like you could with a dog. Presumably, I've never had a dog. Anyway, just an interesting thing to note. People think you can't train cats, and, like, you can't really train them to respond to voice commands, but that doesn't mean you can't train them. But, anyway. Aren't cats less domesticated than dogs? I don't know. I personally, I don't attribute that to a difference in, like, degree or severity of domestication. Basically, anything that doesn't confront a human in a hostile manner, I would consider to some degree to be domesticated. But, now with cats, it's like, I think what you see in cats is the difference between a pack animal and a solitary hunter, primarily. Like, dogs are pack hunters, and therefore, in order for, like, from an evolutionary perspective, a dog has to be responsive to its pack. So it has to be responsive to the social cues of its pack. And, like, the domestication process on dogs is like, okay, and now you have to also use those circuits for us, please. Cats they're not really that kind of social animal, but that doesn't mean that they're not social, right? Like, cats do form, hierarchies of dominance within the household, and fortunately, like our big 15-pound cat, I think I think at this point he believes himself to be above the baby in the social hierarchy, but because of that he sort of takes a protective role over the baby. It'll be interesting when the baby's old enough to challenge his dominance. But anyway, because he's a big cat and he can do some damage if he wants to. But anyway, we should talk less about cats and dogs and more about computers. Oh, you hapless meat computers of a fancy variety. So, anyway, we should talk about the course and stuff. Hello and welcome. Welcome to 1XC3 once again. This is our 8th. I'm working on lecture 10. This is our 8th lecture of our stint here. Announcements. Nothing in particular. There was one thing that I wanted to talk to you guys about that I forgot to mention last time. Yeah, protective cat. Yeah, he's a cool guy. He's a cool guy, Mars. He's the big fluffy guy. He's actually half Bengal, half Maine Coon, which is interesting because, like, Bengals are like a hyper intelligent cat breed, and Maine Coons are just just massive and very, very good natured. So you have this massive, intelligent, good natured cat. Oh, are you back again? Anyway, so one thing I wanted to mention about the stuff that we were talking about in the last class, one of your TAs, Mark Daniel, right now he is on a co-op position working for IBM. I think I may have mentioned this at some point, but he thought it was pretty cool that the specific tools that we were discussing in lab, and also in lecture, gconf, gcov, those tools. Those are tools that he's actually using in his actual co-op to do actual work on Clang, which is the IBM version of the C compiler. So, yeah, no, that's like... So if you wonder whether the tools that I'm teaching you are practical or not, they are actually used. I got confirmation of that from Mark. So yep. Anyway, so we should talk about pointers in C, just to quickly recap where we were. So a pointer, I'm going to say this a very large number of times so that you can get that sunk into your skull. I want you to take a hammer and chisel and engrave these words into the inside of your skull so that your brain always knows them. Pointers are memory addresses. All right? So there are two things that C needs to know in order to hold this memory address, right? Number one, it needs to know that it's a memory address. The way that we tell C that a variable contains a memory address and not a value is by using the star character. You may consider this pointerization. We are taking an integer and we are making it into an integer pointer. So that's one. The second thing that C needs to know is it needs to know how big the amount of memory you're pointing to is. It needs to know the size of the thing it's pointing to. It needs to know this for various reasons. Basically, without knowing how big the thing is that you're pointing to, you can't usefully do pointer arithmetic. We're going to get into pointer arithmetic. So, it needs not only to have the fact of it being a pointer described, it also needs to have the fact of it, the fact of how big that pointer is being described. So, fine, good. The way that you display a pointer is by using %p inside of a format control string. So, in general, stylistically speaking, it's preferable to put the PTR or some kind of indication that the variable is a pointer inside of the pointer name itself, like the actual name. That way, you can, at a glance, look through your code, see which things are pointers, which things are not pointers. It just makes things more clear. Some companies actually have, depending on where you work, companies will sometimes have naming conventions for variables inside of... I didn't turn my light on. They sometimes have naming conventions for variables inside of code that, is shared among people, which is pretty much everything if you're working at a company. And the naming convention will often include the data type of the variable inside of the name itself. It's a useful thing. It makes it longer to type out, of course, but it's useful to know what data type you're dealing with at all times, right? Especially considering the declarations of these data types, or these declarations of these variables, can get quite far away from their actual use in terms of the code. So it's useful to keep that kind of information present in your brain. Yes. So I think I'm skipping ahead of the slides just a little bit. Yeah, I am. Okay. Have I got my email open? I do. Let's close that so I don't get dinged at. Okay. So, like a lot of things in C, uninitialized pointers contain junk data. A pointer will initially point to a random memory cell, probably the first one, 0, because most uninitialized memory, most of the time, something that's uninitialized will acquire the value of 0 simply because that memory hasn't been used since your computer was set or reset. However, you can't rely on that. So it is better to think of a pointer's initial value as being random, some random memory cell in your RAM, with a high probability of it being 0. Either way, address 0 is outside of the memory that's being allocated to your process anyway, so if you try to access memory cell 0, you won't get anything anyway, because it's probably being used by the very, very first startup routines that your computer initializes. But I don't know that much about it. So anyway, when you initialize a pointer, we prefer to initialize them to null. What's called null, a null value. Null is it's a symbolic constant, which is defined in a number of header files. You can grab it from stdio or standard def, whichever you like. A number of other ones as well. In terms of evaluation, null is 0, right? Null has the physical value 0. However, saying null is preferred to 0 for stylistic reasons. So rather than calling things 0 pointers, we call them null pointers. So let me just initialize my pointer to null. So in the same way that you should habitually initialize any variable that you declare to some value that makes sense, you should habitually you should habitually initialize a pointer to null as well. Did I talk about void pointers yet? No. No, I was going to. Okay, we'll talk about that. So, null pointers. Null pointers are, like, think of it as a pointer that you haven't assigned anything useful to. You should, like, checking to see if a pointer is null is actually something you'll have to do fairly frequently. When we get into dynamic memory allocation, if you request memory from the operating system, if that request is refused, the operating system will give you a null pointer back. So you should always check. You should always check to see if you've been given a null pointer if you're being allocated memory inside of heap memory rather than inside of stack memory. So we've talked about the nouns. Here come the verbs. Now we know how to store a memory address, but what good is that if we have no memory addresses to store? Introduce the ampersand, or address of operator. Applied to any identifier, it returns the physical memory address of that identifier. And this includes pointers. So, if you, like I've already got it going on here, we've got x, right? If we want to see the memory location at which x is stored, ampersand x. Store that value in x pointer. Then, when we execute gcc pointers.c a.out, because I'm too lazy, you can see that the memory address at which this x is being stored is 7FFE8E5C391C. That is a hexadecimal number. If you run it again, you'll notice that this is now a different segment of memory. Although you can tell by the first, the first 4 hexadecimal digits that we're kind of, in the same ballpark of the memory chip, but it is a different segment of memory. So you can access the memory address of anything in this manner, including other pointers. Now this is where people's brains start melting. So let's be careful with our semantics as we discuss this. Lots of people think of pointers as being arrows that point to another cell, right? That's not super accurate. That's not the best or most accurate way to think of it. What you should think about, the way that you should think about it, a pointer contains a concrete value, which is a memory address. It is a number just like anything else. The thing that provides the arrow is the pointer dereferencing operation. Okay? So the arrow is an action. Arrows are actions. But the thing that it's acting on is a concrete value. In fact, because it's a concrete value, it turns out we can do math with it, which means we can manipulate our pointers to be able to trace through our memory. That's where pointer arithmetic comes in. That doesn't work unless pointers have concrete numerical values. But this idea that pointer is an arrow, it's like a pointer as it's being dereferenced is an arrow. So let's talk about that. Let's talk about pointer dereferencing. Oh, well, anyway. Yeah, so the correct way to think about this is if you have y, it has a location in memory. If you assign that location in memory to a variable, it just gets assigned to that variable. You can then follow that memory location to its actual physical location to retrieve the value, but that's and that's called pointer dereferencing, for fun and profit. The inverse operation of address of is pointer dereferencing. This is a little confusing, but it's also the star character. So star character declares pointers, star character also dereferences pointers, but it does different things in different contexts. As veteran Python programmers, you should be used to the idea that things can do different things in different contexts. So that's where we get this line here. So by prepending the pointer with the dereferencing operator star, when we attempt to print the value, we follow this memory address to, we open up our memory, we say, okay, give me the thing that's at this address, and as a return result, we get the dereferenced value, which in this case is 6, because 6 is what we are finding the address of. Cool. How are you guys for that? How, like, thumbs up? Are we good so far? What's our viewership like today, actually? 15, not bad. Not bad. I'd like to get a dog, actually, but we have a rule, 1 new animal per year, maximum. Thumbs up. Okay, Ryan's got thumbs up. Okay, so far. Good. Okay. Pointers themselves are not, like... It's a big conceptual leap to start thinking about manipulating memory addresses directly, but if you understood the stuff that we talked about with, like, aliasing in Python, that's, like, we're in the same ballpark, right? So, the deadly and dreaded seg fault. Dereferencing a pointer that points to memory outside of your program's allocated memory space causes a fatal runtime error called a segmentation fault. This is most common with null pointers, but it can also happen if you mess up your pointer arithmetic. Okay, human. Huh? Before you hit compile, listen up. You know when you're falling asleep and you imagine yourself walking or something, and suddenly you misstep, stumble, and jolt awake? Yeah! Well, that's what a seg fault feels like. Double check your damn pointers, okay? There you go. So, seg faults are really easy to produce. If you, if you give it basically any value other than one that was derived using an address of operator from memory that you have access to. Oh, I need to compile that. Warning, assignment makes pointer from integer without cast. So the GCC is already telling me that I'm doing something I probably shouldn't be. Segmentation fault, core dumped. So I'm trying to access memory that doesn't belong to me, right? That's why every single pointer that you ever work with, its value will be derived from either a function like malloc, we're going to talk about malloc, or from using the address of operator on something that is inside of your memory space. You should never use literal values with pointers unless it's null and you never intend on dereferencing a null pointer. I just spilled tea on myself. Hooray. So, ampersand and star are inverse operations. So, interestingly, if you printf x is equal to d, new line, and so you can print a pointer as an integer. It'll just print it as an integer, right? Oh, I need a there we go. it'll just print it out in decimal, right? Except that it's not long enough, but you know. But it'll truncate it and it will try to print it out as a decimal. So if I dereference this guy, which is already an address, then let's see here. There. X is equal to 6. Right? So, and also, if you haven't gotten this so far, these guys are prefix operators, just like the negative sign, and just like bang for not, exclamation point for Boolean inverse. These are like you don't put the ampersand after, you put it before. Same with the dereferencing operator. So, one undoes the other. We extract the memory address, we follow the memory address back to the original thing. So, yes. This is the output for that. Yes. So, the other way, if you try it the other way around, this is kind of interesting. So, if you try ampersand dereference, this will cause an error. First of all, it thinks that this is multiplication. This is another problem with overloading your this is another problem with overloading your symbols in your programming languages. So star is also multiplication. If you use star as a prefix operator, it's pointer dereferencing. But because this is between things, it thinks that this is multiplication now. So, you know, just, you know, use it the way that God intended, basically. And by God, I mean Dennis Ritchie. So, now we start getting into the nitty-gritty. Arrays of pointers. It can be easy to think of pointers entirely symbolically and forget that they too have concrete values in memory. Pointers may be collected and organized in arrays just like any other data type. So, we can have an array of pointers. Each one of those pointers can point to something. So long as we know what the data type is, right? Each element in the array is a pointer to a character array. So in this particular example, so we've got a char star suite 4, and we've got hearts, diamonds, clubs, and spades. The fact that our array contains pointers instead of the character arrays themselves means the character array's memory is managed separate from the array of pointers. So, you know, suit element 2, clubs, that memory is like the array that contains the pointers doesn't care one whit about what that pointer points to, how big it is, or anything like that. All it is it's like, I got a pointer. You can follow it if you want. I don't care. And this has some interesting effects. If you're declaring a two-dimensional array of integers, for instance, if you're, you know, doing something like that solitaire program I was showing you guys last lecture, you know, the board in that game is represented using an array of integers, right? A two-dimensional array of integers. Two-dimensional arrays must be rectangular, right? Each subarray within the array must be of the same length. Because, and this actually gets to why, like, this gets to how memory works in general in C, and also in general everywhere else, but, you know, in C. With an array, the way that C maps the coordinates that you give it in a two-dimensional array to actual memory is it has to linearize it, right? Oh, my camera stopped working? Okay. So, probably because I banged the table. There we go. So a two-dimensional array in our brains is rectangular, right? However, in memory, you should think of everything as being linear. Everything is linear. Think of memory as being a tape that starts at 0 and continues to, 8 billion or however many individual memory cells you have in your RAM, right? Think of it as a tape. This is, the reason that this is the case, actually, is that memory was originally a tape. If you think back to, pictures of old computers that you may have seen in James Bond movies from the 60s and 70s, the way that memory was stored back then was on magnetic tapes, very similar to cassette tapes. I don't know if you guys are too young to. Yeah, you guys are probably way too young to remember cassette tapes, but essentially you had a magnetically sensitive ribbon that was spooled onto two spools, and you put it in a machine, and the machine gradually unspooled it from one side to the other with a little read head that read the magnetic. It read the state of the ribbon, the magnetic signal inside of it, and that's how data was transmitted to your speaker, and that's how a cassette tape worked. Computer memory used to work the exact same way. It's kind of interesting. One of my friends has an interesting hobby of digging through electronics recycling bins, and through doing so, we actually found some of these big spools of magnetic tape that used to be the university's database, and they were using these big spools of magnetic ribbon right up until the mid-90s, which is hilarious because CDs were definitely invented by then. But anyway, so the model of memory that we use is a linear one, right? So, your hard drive considers itself to be linear. Your RAM considers itself to be linear. So the way that two-dimensional array works the way that a two-dimensional array works is basically it's just a bunch of one-dimensional arrays done consecutively. And the way that C knows, it knows where, row 2 starts and stops because it counts along X number of arrays, and then it starts counting inside of that array. So that's why it has to be rectangular. If you're declaring upfront the size, it must be rectangular. However, I'll answer your question in just a minute. However, if your array only contains memory addresses, the things that those memory addresses might point to can be anywhere in memory. They can be in disjoint memory. So, as a result, you can have arrays that are not rectangular. You can have jagged arrays, which is a big innovation, believe it or not. So, aren't floppy disks like cassette tapes? Un petit peu. So, floppy disks are essentially, they're certainly much more like hard disks than, floppy disks are, actually, they operate basically the same way as a CD, except, it uses a magnetic surface similar to a hard drive, rather than, with a CD, it uses little divots in the plastic itself to either reflect or not reflect light as a laser passes over it. With a floppy disk, it was a magnetic read head that you would spin the disk and you would read in the disk like a record, like a phonograph record. and read the disk that way. So you could fit much more, like your information density was much higher on a floppy disk, but couldn't be as high as something like a hard disk, because in order to have a hard disk have such high information density, it has to be like isolated from dust and magnetic effects. Like, it has to be put in a casing that protects it from the types of like mechanical and electrical disturbances that would wipe data. Like, if you run a magnet over a floppy disk, you lose all of the data that's inside of it. And these disks will demagnetize slowly over time of their own accord. So, but still a better solution than the magnetic tape. A higher information density than a magnetic tape, though probably less stable. Like, I haven't listened to a cassette tape lately, but I imagine they're not faring very well. Particularly the cheap ones. They're probably getting pretty grungy sounding because of the magnetic degradation and decay. Anyway, so this is how it works, right? You've got an array. Each one of these array elements points to another array, in this case a character array. These can be anywhere in memory. They can have as many elements as they want. They're not constrained by the size of the original array. So, proud and practical pointer passing. All arguments are passed by value in C, unless the value you pass is a memory address. Well, except even in that case, you are passing the value of the memory address, right? However, once you get it inside of your function, you can follow that memory address down to the variable that was originally passed. So what we can do is we can do pass by reference inside of C, but we, the people, have to pass things by reference manually, which means passing the values of references. So, let's say we have a function, and we pass it the address of foo, and we pass it bar without the square braces. We use ampersand to pass the address of foo, but bar is already a memory address. So I've already said this like a number of times, but arrays are memory addresses, right? The way that an array, the array itself, is manipulated and used inside of C as a memory address. To be most specific, it is the address of the first element of the array. That is what the array without the square braces is. Inside the function foo, inside the function definition, foo will need to be dereferenced, but bar will not. In fact, believe it or not, the square braces, when you apply it to an array, that is a dereferencing operation. That's pointer dereferencing with an offset. That is how an array works in C. So bar doesn't need to be explicitly dereferenced because you're already dereferencing it when you ask for a specific argument from it. Here's an example. Cube by reference. So let's say we had a number, 5, and a function cube by reference. Takes an integer pointer and pointer. So we say star n pointer is equal to star n pointer times star n pointer times star n pointer. That's a lot of stars. So this is important, right? The dereferencing operator does not just work on the right side of the equal sign in a statement. You can also use it on the left side of an equal sign. So you can assign to x through x pointer. So you just have to dereference the pointer, right? So if I say dereference x pointer is equal to 8, compile that, run that, you'll see everywhere previously where it was 6, it is now 8 because we have assigned the value as being 8. So there you go. In Blockovision, this is how this is working. So we have number is 5. We have a declaration for cube by reference, where pointer n is undefined because the function hasn't been called yet. Cube by reference is then called. N pointer becomes a pointer to the original number. Then the final value is calculated, and the 125 is placed inside of the memory cell that belongs to main. Think of these as being stack frames, right? This is main's stack frame. Number is an automatic variable within the main stack frame, which automatic variables are local variables, remember? So you've got automatic and external. That's local and global in C. So pointers can reach into the stack frames of other functions, right? It can extend its hand and pick up memory that is in someone else's stack frame. It just has to have an address for it. Cool. In order to accept a memory address as an argument, the fact must be specified in the argument's type information, obviously. In this example, we replace the following operations. So, passing num by value to cube reference, compute the cube and return it to main, assign the return value of cube by reference to num. So, basically, we're saving 2 assignment operations, right? Or 1 assignment anyway. With this, we just pass the address of num to cube by reference, and compute the cube and store it directly in the memory address provided. Stylistically, pass by value is preferred unless the situation explicitly calls for pass by reference. Passing by reference in this way violates the principle of least privilege. So, while it's a cool thing to be able to do, we are starting to get away from our good programming principles. Remember that, like, the input-output distinction requires effort on our parts to maintain. Like, the idea of input and output is extremely, extremely valuable. And it's, like, you know, you might think, well, in a computer, everything is input and output. But the degree to which we mix input and output up, that is on us as programmers. And the more separate we keep input and output, the better off we are in terms of trying to understand our own programs and other people trying to understand our programs. There is also a programming principle called the principle of least privilege, which we've been exploring that more through the Unix side of things. Last class we were talking about the permission system in Unix specifically. But basically, the idea of the principle of least privilege is don't give anything any more privilege than it needs to perform its task, right? So, for example, Solitaire doesn't need your printer, right? Something that, like a background process, doesn't need your screen. So don't give it access to it. Not only does this prevent stupid people from doing bad and wrong things, like, for example, if every one of you had sudoing privileges on the Pascal server, you could accidentally delete the work of all of your classmates very easily. And you could also do so So you're protecting both against stupidity and malicious intent by restricting privilege to only that which is necessary for a thing to operate, to perform its operations. And it's, you should always think of any program, once written, as being something that needs its privileges restricted. Absolutely. So, so how are we doing? I'd like to check in. You guys following so far? We good? We cool? Yeah? Or nah? You know what? Sometime I would love to give a lecture, like, just on memory. Like, how physically memory works, you know? But I suppose that means I should be teaching in the ECE department rather than the CAS department, eh? Cool. All right. Wonderful. So let's talk about this. Yeah. Let's talk about this thing where arrays are pointers. So the syntax for passing an array as an argument to a function is the same as passing a variable by reference. This is because the compiler does not differentiate between pointers and one-dimensional arrays. Oh, I do have a question. What is the application of pointers? Very good question. What is the application? Why should I care about any of this? Well, there are a few things. First of all, in order to use any of the standard library functions on strings, you need to know how to use pointers, right? So after this, we're going to have a lecture on how to do file I/O and how to work with strings, and it all presupposes that you have some idea of what a pointer is. So that's number one. Number two, pointers allow us to create dynamic data structures, whereas previously all of the data structures that we've done are static. Once you know how to use pointers, you can design dynamic data structures. So the amount of memory that your computer uses can grow or shrink as the program progresses, rather than being fixed at the beginning of the program. That is, like, again, that's, I guess, still a little bit abstract, but let me point it to you this way. Let me point it to you this way. Let me put it to you this way. Do you prefer working with arrays in C or lists in Python? If you prefer lists in Python because they're easier to work with, the only reason that lists in Python work is because of pointers. They're doing a heck of a lot of background work. Like Python is doing all kinds of background work to make lists work. That's all pointer stuff, right? So when we're learning C, if you expect to be able to do the same sorts of things as you do in Python, you're going to have to use pointers to do it. So yeah, pointers are pretty essential. Yep. So yeah, dynamic memory allocation, knowing how to use standard libraries. Basically, every single thing that we're going to talk about in the course after this lecture, with respect to the C stuff, is going to need we're going to need pointers for it. So, yeah. You can even have function pointers. But we're not going to talk about function pointers. So, the compiler does not differentiate between pointers and one-dimensional arrays. Like so many things in C, that means it's your job. It's up to you to write your functions so that they are using their arguments as intended. Documentation is critical. So, there's nothing in the C compiler that prevents you from using a pointer as if it were an array. If you do it, then you'll probably get a seg fault. But if you get a seg fault, that's your fault, not the computer's fault. At least that's the attitude that C takes. An array is actually a pointer to its own first element. We've already said that. We can perform arithmetic to traverse arrays without the indexing operator. So let's talk about const. Whenever we work with pointers, there's a possibility of pointer misuse resulting in a seg fault. We can prevent arguments from being modified by using the const qualifier. So if you declare an argument constant, that means it can't be changed by the function. That is, in Unix file system terms, that is disabling write privileges for that variable for that function. Again, this comes down to the principle of least privilege. This is a good way to enforce principle of least privilege. If it's a pointer, that means here's the pointer, and don't touch it. You can dereference it. You can even assign to the dereferenced. You can even assign to it, you can assign to the dereferencing. So you can assign to the original memory cell, but you can't modify the pointer itself. If you try, you'll get error, assignment of read-only location. Using const to restrict functions from modifying things they shouldn't modify is good software design. In general, a program should only have enough data access to accomplish its task, and not one smidgen more. So there we go. So, let's talk about pointer arithmetic. We're doing pretty well, actually, for time. I was worried that this lecture would be, way too long for the time slot. I kind of like the experiential element, the way that this is an experiential course. I'm not gonna lie, though, being restricted to 2 hours of lecture per topic is, there is stuff I can't cover, and it bugs me a little bit, because I'm doing as close to a full treatment of C as I can, but there are, necessary restrictions, you know? Same thing on the Unix side. But anyway, I do kind of agree that neither C nor the Unix stuff would be a full course on its own. I do agree that they should be combined. It's just, I wish this were I had, 120% of the time for this course, you know? But anyway. So here's a comic. It's kind of tiny. Hey C, could you zero out the data at these addresses? Sure thing. Poof. Wait, what data did those addresses point to? Looked like some kind of critical OS data, kernel or some such. What? Meh. C, that's the attitude that C takes. C will do anything you ask and not think about it. C doesn't think about things. No clever quote this time, though I did learn that the internet seems to think that indirect means passive-aggressive. I was looking for, puns about being indirect, and it's passive aggression, and I'm like, that's not what I mean. Anyway, so a program illustrating array addressing. So, is that so? Come here. Fine, be that way. She just comes up to me and starts yelling at me. Jeez. Anyway, so we've got two arrays in this program, foo and bar. Foo is an array of integers. Bar is an array of what look to be floats, although it looks like they're also shorts. Interesting. So we print the one, and now we're printing the other. The address of each element in each one of these arrays. If we print the address of each element of each of these arrays, you will find that the one that is typed int goes up by 4 each time. The one that is short goes up by 2 each time through the hexadecimal numbers, right? Like A is 10, C is 12, E is 14, right? So memory addresses are addressed to the byte. Every byte has its own separate memory address. When you look at the memory addresses of integers, they must be 4 bytes apart, because the memory width of an integer is 4 bytes. Short ints are 2 bytes long. That's why they're 2 bytes away from each other. So you may notice a numerical relationship between the position in the array and the pointer given the starting position of the pointer. Right? The pointer, like, arrays hold memory in consecutive memory cells. So, our old friend ++ makes a return. Notice in the previous slide how foo's memory addresses are 4 bytes apart, and bars are 2 bytes apart. The array is continuous memory, and each element is allocated the size of the base data type of the array. Definitely not. I should not quit my day job. If we wish to perform pointer arithmetic to traverse an array, the compiler needs to know how big the steps are. So, character arrays, a character, a char, is 1 byte. Right? So each char, like, each character in a string is stored it's like a byte, a byte, a byte, a byte, a byte, you know? Operators can mean different things when applied to arguments of different type. Float versus int division, for example. ++, when applied to a pointer, will automatically take the size of the data type it's operating on into account. So, let's do some stuff here. Int y is an array of 10 elements. 1, 2, 3, 3, 4, 5, 6, 7, 8, 9. There we go. So, let's just there we go. Print so for I is less than 10, or no, int I equals 0, I is less than 10, I plus, postfix ++ on the pointer. Well, actually, let's make a pointer for that itself. So int star y pointer equals null equals address equals y. There we go. We don't need address of because it's already an array. So let's take a look at why is it not compiling? Because I didn't use that. There we go. Void pointer. No. Oh yeah, pointer. There we go. So, expected. Oh, forgot the comma. There we go. So in order to manipulate this pointer, like, although the array itself is a memory address, modifying that memory address for the purposes, even for the purposes of demonstration, isn't a great idea because, like, the operating system has allocated that array some memory and it's like given it to that variable. So you shouldn't mess around with that too much. So in order to traverse the array, it's always a good idea to use a variable other than the variable that contains the array, like, to which the array itself has been bound, is another way of thinking about it. So we compile, we execute, and you can see we are also increasing by 4 each time. Ho ho! You may notice also that things tend to be lining up with, like, you know, all the numbers are even. That has to do with the way that your file system and your computer deals with memory. 64-bit operating systems, Maybe they like to deal with memory in specific chunk sizes. Maybe it likes to deal with memory in terms of the word size of the operating system. Yes, they think it does. So plus plus. This this is array indexing, right? If you dereference this guy, you get y at I, or d I, there we go, well, is equal to, and we'll put that there. Boop, 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 boop. Dereference y pointer. There we go. Yes. Oh-ho! We seem to be exceeding the bounds. That's not good. Interesting. We seem to have an off by 1 thing. Let's see if we can fix that. Yeah, there we go. There. So yeah, we can access the elements of an array using pointer arithmetic straight. We have straight pointer arithmetic. We don't need the square braces. That's because the square braces are, in fact, just syntactic sugar. All square braces are, like, we'll get to it. There's a slide on it. But anyway, so, traversing an array with pointer arithmetic. This is a cool little program that, so you've got a character array, dated reference, and we have a pointer to that. Notice we're not using the address of operator because it's already an address. And while the pointer is not null, this is what null, like the null character, right? Because this is a string. All strings are null terminated. We print parentheses with the character in between. We're dereferencing it and we're incrementing it, and then we print a new line, and then the result is that you get this kind of typewriter-esque looking thing right here. So, there's a question. So, for the assignment, when it says in Q6, start is the memory of the stack, the whole stack is stored in there. So the stack, yeah, let me read the question. Let me read the question. That might be... I don't want to say something that's wrong accidentally because I didn't read the question first. Because, you know. Building a stack using pointers and dynamic memory allocation. The base type of the stack will be long int. Our stack will be defined by two pointers, start and end. Start is the pointer to which the stack's memory will be allocated. End is the end points to the first memory cell after the end of the stack. So, yes. Please consider the element at the end of the array to be the top of the stack. So, basically, so for those of you who actually watch the lectures, this will be a huge hint for the assignment for you. The stack question, it's like, build me an array that has two pointers instead of one. The first pointer is the bottom of the stack, right? Start is the bottom of the stack. Start points to the bottom of the stack. End points one past the end of the stack, right? So if you've got like if you've got, let me just draw it out here. So if you've got a stack that looks like, you know, 5, 4, 3, 2, and then like null or 0, right? Like some sort of non-element. Start points here. End points here. Right? So when you are allocating, so essentially, if you want to pop the top element of the stack, you have to look at the thing that's one closer to start than end, right? Pop that, replace it with the null, throw it in there, and return the value you're popping. That's a pop operation. If you're pushing, this value gets overwritten, and end gets incremented to the next pointer. The trick, or to the next element. The trick with this is that you're going to have to use dynamic memory allocation to allocate this, or else you're going to run into seg faults. We're going to talk about dynamic memory allocation very, very shortly. But that's a good question. Thank you very much for that question. So, before we get to dynamic memory allocation, let's talk about the other pointer operations that we have available to you. In addition to plus plus, you also have minus minus, plus minus, plus equals, and minus equals. In each of these cases, the number you are adding or subtracting to or from the pointer is implicitly multiplied by the bit width of the data type. Let me finish this slide. So, if you say pointer plus equals 4, that means you are jumping ahead 4 memory cells, based on whatever the data type the pointer carries, right? So, for example, if pointer points to an integer, then pointer plus 4 would move the pointer 16 bytes, since the bit width of integer is 4 bytes. Pointers may also be subtracted from one another, but only meaningfully if they point to the same array. Pointer A minus pointer B yields the number of array elements difference between the two pointers, not the number of bytes difference. In practice, pointer subtraction is almost never useful, so I wouldn't spend a lot of time memorizing it. So do you have to make a stack and have start and end point to those? Yeah, well, the whole point of the stack question is that the stack is created through push and pop operations, right? Yeah. Yeah. So, some words to the wise. In the previous example, tracing a character array, we used our knowledge that strings are null terminated to set a stopping condition for our loop. Pointer arithmetic can easily place a pointer outside of the bounds of its original data structure. There is no built-in protection against out-of-bounds pointers, so we can easily use them to assign to memory outside of the array bounds. So you have your stack frame. You have a certain amount of memory that's been allocated to you. If you have a pointer that leaves the bounds of the array, it will trace through quite a bit of our memory before it hits an until it goes outside of the stack frame itself, which is what causes a seg fault, right? So these are things like, other variables, other automatic variables. These are things like I believe the code that constitutes the function itself is stored inside the stack frame. The program point, well, maybe not the program pointer. Certainly, like the return value memory cell is going to be stored inside the stack frame. You can overwrite all kinds of data. Not a good idea. And just because you didn't get a segmentation fault doesn't mean that you didn't do it improperly, right? You can, in fact, if you're only going one element outside of your array, most of the time you won't hit a seg fault, right? But it's still bad. So, this could overwrite other variables, causing segmentation faults and many other troubles. Back in the day, this was actually a common exploit used to hack the government. So, the fact that C could read pointers, outside of, it could assign to things outside of its specified data structures, this was used to hack things. Basically, the system, the principle of least privilege that's built into the Unix operating system was, in fact, a countermeasure against this type of attack. So, we need to talk about wildcard pointers. So normally, pointers require compatible data types to be assigned to each other. There's one, so basically what that's saying is if you try to assign a double pointer, like a floating point pointer, to an integer, the compiler will tell you no, or it will complain at you. The exception to this is a void pointer. Void pointers do not have an associated data type. It's a generic pointer that can point to any data type. Void pointer is compatible with all data types and may be used in assignment operations freely. So basically, void pointer is a way of saying, I don't know what the data type of this pointer should be. But here you go. The catch is that the void pointer cannot be dereferenced. This is because dereferencing uses the byte width of the pointer's data type to select the area of memory to return, right? So, in order to return an integer, it needs to know that it's an integer and not a character. If you have specifically not selected a data type, i.e. you've made it a void pointer, C has no idea how much data to return to you if you dereference that pointer. So it's an invalid operation. Incidentally, the way that you can get around this is that you can cast the pointer, right? You can use typecasting to change the type of the pointer to the type of pointer you need for dereferencing purposes, and then you can dereference it. That's like telling it, okay, we didn't assume a data type up to this point, but now I'm pretty sure this is an integer, so I'm going to cast this as an integer pointer, and there we go. So, equality and relational operators work on pointers. So you can tell if two pointers are the same pointer by using regular equality. Of course, you know, this is because pointers are, in fact, concrete values in memory. So, equality comparison with null is quite common. You often need to check to see if a pointer is null. Array indexing is actually syntactic sugar for pointer arithmetic. So foo at 3 is actually star, or dereference foo plus 3. And if you have understood this, you now know why everything in a computer uses zero indexing. This is why the first element of an array is 0, because it's foo plus 0 dereferenced. It's because pointers point to the first element of the array without modification. This is a modification of the underlying pointer, and every programming language uses it this way because it's the convention, because it's how memory works. Congratulations. You now know why zero indexing. But you see how we couldn't, like, I couldn't tell you this to you when you had only known Python. It wouldn't make sense, you know? It wouldn't make sense using only Python knowledge. Now it makes sense. The reason that everything is zero indexed is because the index modifies the pointer, and the unmodified pointer is element 0. Anyway, so, therefore, it is also possible to index pointers in the same way as arrays. One of the few differences between pointers and arrays and array identifiers is that array identifiers may not be assigned to. We can think of them as read-only pointers. So there you go. You basically don't have write privileges if it's been declared as an array. There are slight differences between arrays and pointers. However, it's mostly it's like the little amount of work that C does on your behalf distinguishes arrays from pointers. I'm sure that the original like C72 didn't have arrays, it just had pointers. Although, you know, maybe I'm wrong about that. Maybe that was like one of the big innovations of C versus like B or BCPL. Anyway, so how are we doing? Give me a thumbs up. Are we cool so far? Because we're going to talk about dynamic memory allocation. So, as I talk about this stuff, I will attempt to relate this back to the stack question from the assignment. For the benefit of all of you awesome people who are asking me, how the heck do I do this assignment that you have assigned me? It's kind of tricky. It's like, normally I don't like assigning an assignment if, like, the material that you need to complete the assignment hasn't been covered yet. I don't like doing that, because it's like, you know, it rankles me. But with this particular one, like with the compressed course timeline, like there was really no other way of doing it, unfortunately, because it's got to be covered. So, yeah, okay. So we got 2 people paying attention. So, 3 people paying attention. That's cool. That's the same number as last time. Let's see. Cool. So, dynamic memory allocation. Up to now, our array sizes have been hard-coded, that is, set in the program code itself, not at runtime. In this section, we will learn how to allocate memory dynamically, allowing us to expand or contract arrays as needed at runtime. So, dynamic memory allocation means exactly what it says. We are changing memory allocation as the program runs based on the values that are being calculated, rather than statically everything being done up front. When we use static arrays, these memory operations are implicit. So we are going to learn how to use the memory operations that C itself uses to establish static arrays. When you declare a static array in C, you are using these operations implicitly. However, by using them explicitly, you can do more interesting things than just the built-in C constructs. The general procedure is to declare a pointer, invoke a memory allocation operation, and store the resultant memory address in the declared pointer. This isn't actually that difficult. It's just, once you get it, you'll be like, okay, I get it. So, we will learn how to use the following functions, which are all contained in standard library.h. stdlib, malloc, free, salloc, or calloc, and realloc. These stand for memory allocation, free, calloc, I don't know, and memory reallocation. So, malloc, the basic one. This is the Mario of dynamic memory allocation algorithms. So, dynamic allocation of a single large block of memory given a specific size, or a specified size. So, if you give it a size, it will allocate that many bytes. malloc accepts as an argument the number of bytes to allocate expressed as an integer. So, if you want 100 integers, it's 100 times size of int. If you want 100 floats, it's 100 times size of float. If you want 10,000 characters, it's 10,000 times size of char, right? malloc produces a void pointer, which may be typecast to the type of pointer you wish to store the address in, right? This is a typecast. This is how you change the type of something in C. Sometimes this will also do something semantically to it. Like if you typecast a float as an int, I believe it truncates. But yeah, this doesn't really modify the value of the pointer that's being returned. It merely tags it with the size that you're trying to allocate to it. So let's do this. Let's try this out. Oh my god. Just gonna do that there. So, let's say we have not start, right? Or no, this isn't. That's mean. Just some memory. We want to allocate that, so that's an int star, so that's a pointer to some memory. Malloc 500 times size of int. if we try to compile that, we get a warning. Incompatible implicit declaration of built-in. Oh, I also need to include... okay, that's the wrong warning. Include stdlib.h. There we go. Try to compile that now. And it compiles. So, if you wanted to work with this, some memory at 0 is equal to 9, whatever. Printf d some memory 9. Let's do something more interesting. Size of some memory. Semicolon. Wants a long integer. All right. 8. Interesting. So that's because it's giving me the size of the pointer, right? So the size of the pointer, an integer pointer is 8 bytes. So there you go. And like this is again sort of coming down to this issue of things not knowing how big they are in C. But anyway, so malloc allocates this chunk of memory to the pointer. This is how arrays are given. When you declare an array that has like 100 values, but you don't give anything, you don't give any initializing value to it, this is what you're doing. This is like syntactic. That is syntactic sugar for this. So you do need to typecast it though, and you typecast it by specifying int star or int star. Like that. There we go. So, malloc may fail if the requested memory is larger than the available memory. If it does, it returns a null pointer. You should always check a pointer returned from malloc for null status before using it. So, if some memory is equal to null, return -1 from main. Non-zero exit status. Yes. So, malloc allocates the number of bytes specified to the pointer. There are no free lunches in C. Now we know how to allocate memory, so let's talk about deallocating memory. Memory manually allocated using malloc must be deallocated manually as well. To deallocate is to take memory allocated to a program and return control of that memory to the operating system. So I've actually, like by running this a few times without having freed the memory, the memory is now just floating in my operating system. It's floating in there. Well, it's floating inside of my memory chip. It's not being used by anybody, but the operating system still thinks that it's being used, right? Because the operating system keeps a table of all of the memory that's been allocated to every process, right? And that was never, like, my C program never said, I'm finished with this memory, you may use it for other purposes, so the operating system will hold on to it for as long as your computer hasn't been reset, essentially. So in order to free that memory now, I'm going to have to restart my computer. Fortunately, it isn't much memory, so it doesn't constitute much of a loss in terms of my, general operation. But you always need to free everything. The free function accepts a pointer as an argument and deallocates the memory pointed to. While it is not enforced by the compiler, freeing dynamic memory is the same as closing file streams. Very good practice. So, free some memory. There we go. Can you use malloc in question 6? Yes. So if the stack has nothing in it, malloc is the correct way to initialize it, right? If the stack has stuff in it, realloc is the correct way to modify the size of it as you go, right? We're getting to realloc. So yeah, you want to free memory that you have allocated. Example using malloc and free, malloc demo. So we assign n, however much n is, we assign a pointer of that size times the size of the integer. If it's null, we print runtime error and exit. The memory is location allocated is x. We then print everything there. The allocated array is etc., etc. So yes, anyway, we're starting to run short of time, so I want to get through this to realloc because that's going to be important. So an alternative to malloc is calloc. It's memory allocation for the hygiene obsessed. The primary difference is that it overwrites all of the memory with zeros before it gives it to you. malloc doesn't do that because that takes time. malloc is actually a constant time algorithm, whereas calloc takes an amount of time proportional to the memory it's giving you, because it has to overwrite it. So, calloc accepts two arguments. The first is the number of chunks of continuous memory to allocate. The second is the size of these chunks of memory in bytes. So, additionally, calloc wipes all allocated memory, and aside from these 2 points, usage is exactly and precisely the same as malloc. It returns the same void pointer, for instance. This is how you use it. Number of bytes, or number of memory cells, size of memory cells. Right? So if we assign 5 4-byte chunks, we get 5 4-byte chunks. There you go. So let's talk about realloc. Change it, because I said so. So what if we need to dynamically change memory that's been dynamically allocated? Realloc allows us to change the amount of memory allocated to a pointer while keeping the data already in it. So, if we have a pointer that has been allocated, say using calloc, and then later we want to make that pointer bigger because maybe it's a stack and we're pushing something onto the stack, you use realloc. You give it the pointer that you're reallocating, and you specify the new size for it. The return value of realloc is a new pointer. Might be a new pointer, I should specify. It might be a new pointer, it might be the same pointer, but you don't know, so you have to reassign it back to the original pointer, if that's how you want to deal with it. So, when you have a stack and you push something onto the stack, you have to expand that stack in memory in order for it to not run into seg faults, right? If you have a pointer to an existing stack and you need to expand it by 1 element, this is how you do it. This is how you do it. Again, so the reason the return value of realloc might be the same pointer it might be a different one, it depends on how the memory is arranged. Realloc tries to do things intelligently. So if the memory, like if there's memory at the end of your array that's unallocated, realloc won't move your array. It'll just it'll grab that extra memory and assign it to that pointer, right? However, if there's not enough space for that reallocation to occur, your operating system has to find somewhere else to put it. And when your operating system finds somewhere else to put it, it has to return a new pointer because it's no longer at the old location, it's at the new location. So, yes, the first argument is the pointer to be resized. The second argument is the new size, following malloc rules, not calloc rules. Realloc returns a pointer to the newly allocated memory. Please forgive the spelling. New chunks of memory will be filled with smelly garbage. So, when you realloc, it's very similar to the malloc procedure. All this is basically doing, it's doing three things. It's doing a new malloc, which might get it a new pointer. It's copying from the old memory to the new memory, and then it's freeing the old memory location if it needs to move it. So this is how it works. You have an integer pointer. You've malloced 4 bytes worth of memory to it. Or, sorry, 20 bytes of memory to it. There you go. Pointer has 20 bytes. If you realloc and give it 10 memory cells instead of 5, you now have 40. It can decrease as well. Yes. So, when you're doing your stack question, keep in mind that it's using an end point in the same way that a string uses null termination. So, yeah, just keep that in mind. So, basically, the stack question is, it's basically 2 components. Component number 1 is, can you use dynamic memory allocation to keep up with the pushes and the pops, right? So, when you push, you have to expand. When you pop, you have to reduce. Can you do that? Element number 2 is, can you update the end pointer based on where the end now is? And, of course, element 3 is you need to actually assign to the elements and return from the popped element, depending on whether you're doing push or pop. So, yeah. There we go. Last slide comic. Man, I suck at this game. Can you give me a few pointers? Yes. Ha 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 ha. So, question. Ask me questions. Would you use malloc in question 6 in assignment 1? Yes. In fact, I think that it says dynamic allocation here somewhere, doesn't it? So the other thing is about this question. Let me just explain. So because push results in a reallocation, because push results in a realloc operation and the pointer may change, the pointer itself is an implicit return value of the push operation, right? So push returns void, but the start and the end pointers might change. They're implicit return values. So, yeah, that's one thing I would say. Any other hint for it? Yeah, says dynamically reallocate the stack to accommodate the new size. You should know what that means now. It means use realloc. Any other hints? This question is not actually that long. It's just a matter of knowing how to do it. Like, push and pop. So both push and pop should be you should be able to accomplish that in 10 to 15 lines of code, like at the outside. You know, is empty is very short. Like, it's not a long or difficult question. My goodness. Like, for these assignment questions, they're not really designed to be particularly long. You know, it's going to feel like it takes forever because you're doing it in C versus Python, but, like, basically, if you're writing programs that are hundreds of lines of code long, you're probably missing something. Like, I remember, you know, I had a similar question in I had a similar question when I was doing 2MP3 last year that had to do with date formatting, like format strings and dates. And, like, my sort of instructor solution to that problem was, like, maybe 6 lines of code, and this one student had, like, written, like, 150 lines of code because they weren't using the tools that I gave them in class. Like, you're past the point where everything can just be if statements and the while loops. Like, you need to use the tools that I am giving you. I am giving you gifts. You need to use the tools that I give you. The assignments expect you to have been paying attention to the lecture slides and not think in Python and program in C, right? You have to think in C. You have to use C constructs. You have to use the tools that I'm giving you. Otherwise, you'll, like, it's possible to do these questions not using the tools that I give you, except, of course, with the pointer stuff. Like, it's like if you're not using the pointer stuff, then, you know, you're not going to get the question right. But, you know, if you don't use the tools, then you're not going to have a fun time with it, basically. Yeah, anyway. I'll stop pontificating. Let you guys get some lunch! Take her easy, folks. Don't do anything I wouldn't do. I actually really like the lab that you guys are going to be doing today. Like, I had a lot of fun putting it together, so I hope you enjoy it. I enjoyed it. Take her easy. I'll sign off here.